Hello, I'm Manuel. This is Julius, if you don't know us. Today we're going to present our most recent work on simulation-based inference with foundation models. And yeah, first let's go through what simulation-based inference is, if you don't know it. So in short, it's basically a method to do Bayesian inference, especially useful if like your probabilistic model is implicitly defined. And the steps you usually go through is that you start with some prior, as usual in a Bayesian setting. This can also be implicit here. Then you have some simulator, and this can be any arbitrary computer program. And the likelihood doesn't have to be defined, it's just implicitly defined through the simulation process. So what we need to do is we need to take the parameters and run it through the simulator to create a synthetic training data set. And with this training data set, we then train some conditional density estimator like NPE, usually, that the given XO tries to predict the feasible parameters. And in essence, this then returns the joint posterior distribution. And this is basically then, in a sense, very similar to any supervised learning setting. Just like in regression, you would predict the mean, and here we predict the posterior distribution. What is another feature of the simulation setting is that we can create new data, and because learning the posterior requires quite more samples usually than just learning the mean, one can do this in a sequential setting. So we take what we currently have and then use this initial estimate to propose parameters that are more informative for the problem we currently want to solve. And then we just simulate this more informative parameters using simulator and then retrain or refine our density estimator we have in a roundwise sequential setting. And some pros of this approach is obviously that it's kind of likelihood free. It's like the simulator is just a black box. We don't need to know anything about this. And it's good that it's at least this NPE setting, what's good at this is that it's very fast at inference time, right? The training takes long, but the inference then is fast because it's just a forward pass through this network we learned. And the cons is then that we need a lot of simulations to train it, as I said. We need to do some training, so we always need to choose some hyperparameters or just trust in the defaults. And if we change the simulator, we also have to retrain. And to solve this, Julius will continue.
Exactly. So we're trying to address these limitations, but first we need some background for this. Maybe a quick survey. Who has heard of TabPFN in this room? Okay, so I guess quite a bit of people. So TabPFN, you can really think about it as a foundation model for tabular data. It's like an LLM, but for Excel files, so to say. So usually, for example, if you want to train a regression, you have a training data set X-train and some target labels, Y-train, and you use sklearn and you fit your estimator with that. And after you've done that, you have some test points and you can evaluate your regressor on these test points, right? So there's this two-step process. You first train, then you evaluate. And what TabPFN does through some clever pre-training and is to do this basically in one forward pass. You basically pass the training data set and the labels together with the evaluation points completely into the context of this huge transformer model. And then with one forward pass through this model, you get the same thing. And these are all figures from the original TabPFN paper. And as you can see, TabPFN is quite good here in the second row of fitting all sorts of regression problems in this case. And it even can handle some uncertainty. So it's not a deterministic prediction, but it predicts some density, some one-dimensional density. So really what TabPFN is, but the definition I would give for it is that it's like an in-context estimator for one-dimensional densities, right? And how we now use this foundation model for SPI, Manuel will continue again.
Yeah, so exactly, right? We have now this TabPFN network, which can basically predict any 1D parameter density, and then we can just continue like for any multidimensional posterior distribution, we can basically do the same. We take our context set, put it into context, and then predict the first parameter, then the second, and the third, and this in an autoregressive fashion by extending the context data set and the test points by what we have sampled and what's like in the training data. But the problem is a bit that, like, as usually, like for these kind of models, for these in-context learner, like also LLMs, that the size is usually limited, this context size, and it just gets more expensive at some point. So one can also do is some filtering, that you kind of filter your data set to like the set that is relevant for your current problem. And in an SPI setting, you can do any sort of filtering based on X, but not based on theta. For theta, you have to do some correction. This happens in the sequential algorithms. But there we also in the paper proposed some techniques to make this somewhat efficient. But the major benefit here is, right, that this is just evaluating. This training phase here is completely skipped, right? We don't need to train anything. We just use this in context learning. And yeah, now
so now we need to, now that we have this thing, we obviously need to figure out whether it's any good. And in SPI, there is a thing called the SPI benchmark, which is just like different inference tasks where we know the ground truth posterior. Like we really have ground truth samples. And then obviously you can, on several observations, infer the posterior with different methods and then see how well the posterior matches the ground truth posterior. And the metric we're using here is a classifier to sample test, which basically just works by taking two types of samples. You take some ground truth samples and you take some samples from your estimated posterior and you train a classifier on that. And the idea is if your classifier cannot distinguish between the two, so has 50% accuracy, then these distributions are the same or almost the same. Whereas if your classifier has like an accuracy of 1 and perfectly distinguishes the two, you know that these two distributions are very different, right? So here, the 0.5 is just the accuracy of the classifier, and 0.5 is very good. Then we have perfectly or almost perfectly estimated the ground truth posterior. And yeah, we compare our method NPE-PF to some baseline methods from SPI. The details don't really matter how they work, but as you can see, that like NPE-PF is at least competitive. There are areas where it's better, areas where it's worse, but really what catches the eye is that it's very good if you only have few simulations. So here on the x-axis, we always have the number of simulations that we use to learn the posterior estimator. That's really important in SPI, that you basically use, as Manuel said, as few simulations as possible. And you can see that for the small simulation budgets, like for 100 or 1,000 simulations, NPE-PF has a really good performance over traditional methods. Okay, and this is what we call the simulation efficiency, or that TabPFN, this method is simulation efficient. The same holds basically true for the sequential variant Manuel explained, where we iteratively acquire new simulations depending on the observations. And you can see here again that for the smaller simulation budgets, the performance is quite good. And we also looked at some runtimes. As you can see here, the training time, obviously, for our method is quite nice because there's no training, so 0 seconds. But for the sampling time, because it's such a huge model, it can be slower than, for example, training a direct posterior estimator, basically a normalizing flow. If you have something like this, sampling is really rapid, like super fast. And our method NPE-PF is more similar to some other methods that require some MCMC sampling. So it's not super fast at inference time, but obviously you save a lot of time not having to train. Exactly.
Yeah. And last but not least, we tried it like on a bigger problem. This is like a problem from neuroscience. It's quite high dimensional for SPI problems. Like, right, it's like 31 dimensional. And we want to estimate this 31 dimensional joint posterior distribution. One challenge in this problem is basically that given the prior And then if you take samples from the prior and simulate them, then 99% of them will be completely none or invalid, will be super bad. And because of this, like standard NPE takes like 20 million simulations because 99% of them you anyway throw out. And that's why for this problem, the sequential or several variants of sequential schemes were developed. And these are these baselines down here, like S and V, S and S, U and LE and so on. And yeah, and in this problem, like this NPE-PF or like NP with the pre-trained TabPFN was like very, very outperforming these methods. You can see like this blue line here, basically it already beats the other methods with like, with like 5 times less simulations or something. Or no, like with well, a lot of less simulations. But yeah, exactly. And yeah, it's also right, this is quite easy to use. We like the others per round, basically the other methods have to retrain and all the time, and here we just evaluate basically. But yeah.
Exactly, then we're already coming to the end. So the takeaway is that our method NPE-PF repurposes this tabular foundation model for in-context simulation-based inference. And this really makes it quite easy to use and simulation efficient. Maybe some intuition for this, like it's when pre-training, like in the pre-training, when TabPFN is pre-trained, they also include a lot of like very small data sets. And so to me, it's not so surprising that this is a lot more stable, like pre-training over many different data sets of 10 data points than really doing an optimization on 10 data points. Like you're immediately going to overfit, but with this pre-training from TabPFN, you can gracefully handle these small data sets. And I think that is a large part of why this method is so simulation efficient. Exactly. Then, as Manuel just explained, the sequential variant T-SNAPE-PF offers even higher simulation efficiency, especially also on some usually quite challenging real-world tasks. And there's a lot of other stuff in the paper if you want to check it out. For example, we do unconditional density estimation. You can estimate palm tree Tübingen density with TabPFN without training, which I think is quite nice. You can nicely get the structure. Yeah, exactly. And we're currently rebuttling this, so wish us luck. Yeah. Thanks.